So in this session, we are going to study periodic signals. So let us start. First of all, let us look at the properties of periodic signal. Note that every periodic signal is assumed to exist for all times, right from minus infinity to plus infinity. So that is one of the basic properties of a periodic signal. It exists from minus infinity to plus infinity. Then, as the name suggests, it repeats itself after a certain interval of time, which is called as a period of this periodic signal. Okay. So since it repeats itself, that is why it is called as a periodic signal. And it will not only repeat after this time, but it will also repeat after integer multiple of these times. So all this can be summarized here. It repeats itself after a time t called as the period. And t is the shortest time after which the signal repeats itself. It will also repeat after 2t, 3t, etc. Finally, the third property of this signal is that if you integrate this periodic signal over the entire time period, then it does not matter what are the absolute lower or the upper limits, as long as the time period over which you integrate it is equal to t or even integer multiple of t, you are going to get the same result. So it can be stated like this: area under any interval of t is same. So suppose you integrate xt from the limits to z plus t, where z is some instant of time. So the overall time interval over which you are integrating xt is t. Now if you consider some other instant of time, say w, but the upper limit is still w plus t, then this is still integrated over the entire time period t. So the property is that this area is going to be same as this area. Okay. So these are some of the properties of the periodic signals. Now, suppose we have a number of periodic signals and we add them together. We take their sum. Then the question we ask is, will the resulting signal, that is the signal that you get after adding all these individual periodic signals that you get, is it going to be periodic? So it will be periodic under certain conditions which we will study. So suppose x1t and x2t etc. are periodic signals. Then we form a new signal which is obtained by addition of all these signals. So x1t plus x2t plus etc. up to xmt. Now let t1, t2 etc. be the periods of the signals x1t, x2t and so on. Then xt is periodic with period t if you assume that t is always an integer multiple of the individual time periods. That is, it is given by n1 into t1, or it is also given by n2 into t2, etc. So as long as it is an integer multiple of each of the individual time periods, then xt is going to be periodic, otherwise not. So as we said, where n1, n2, etc. are integers. Now, if you take the ratio of t1 to t2, so t1 divided by t2, you can see by cross multiplication, that will be n2 by n1. So since we are assuming that both n2 and n1 must be integers, these ratios have to be rational for xt to be periodic. If it is irrational, if it is not a ratio of integers, then the signal is not periodic. Okay. Then let us try to find the systematic method of finding the time period. What is the way of finding the time period? So convert each of the ratios t1 by t2, t1 by t3, t1 by t4, etc. to ratio of integers. So note that x1t, x2t and their time periods are known. So t1, t2, t3, t4, etc. they are all known. So we can calculate these ratios, t1 by t2, t1 by t3, etc. Now in their original form, they may not be ratio of integers, but we can convert them. For example, suppose your ratio is 0.1 by 10, then you can also write it as 1 divided by 100. That is what we mean when we say that you convert it to ratio of integers. Okay. Then reduce these by removing common factors. In this particular case, there is no common factor to be reduced, so you don't have to do anything. But in general, you may have. We will see an example of this. So you remove the common factors, then find the least common multiple of denominators of these ratios. Understand what we are doing. We are finding T1 by T2, express them as a ratio of integers, remove the common factors, and then we get some results for T1 by T2, T1 by T3, T1 by T4, etc. And so each ratio will have a certain denominator, and you find the least common multiple of denominators of these ratios, and let this be n1. If that is equal to n1, then the time period is given by n1 into t1. That is the method of finding the time period of the addition of the periodic signals. So let me give you an example. Suppose T1 is 1 by 100, T2 is 1 by 150, T3 is 1 by 200. Then we first obtain, say, T1 by T2, that is 150 by 100. That is, now you remove the common factor, so it becomes 3 by 2. Then find T1 by T3, so that is 200 by 100, so that is 2 by 1. So these are the only ratios we need to have, because we got only 3 terms here. So one ratio will be T1 by T2 and the other ratio will be T1 by T3. So if you compare these now, 3 by 2 and 2 by 1, the denominators are 2 and 1. So you find the least common multiple of 2 and 1, which is equal to 2 itself. So n1 is 2. In that case, t is equal to n1 into t1. So n1 is 2 multiplied by t1, which is 1 by 100. So 2 by 100, that's 1 by 50, that is equal to 0.02. So this is the time period of the resulting signal. Incidentally, note that we have been talking about the time periods of the periodic signals, but we all know that the frequencies of these periodic signals are reciprocal of their time periods. So for example, the first signal is 100 Hertz, the second is 150, and the third is 200 Hertz. So when we add all these signals, the time period that we get is 1 by 50, which means that the frequency of the resultant is 50 Hertz. This is the so-called missing fundamental, because none of the individual members have a frequency of 50 Hertz. However, the time period of the added signal corresponds to 50 Hertz. So that's why it's sometimes called as the missing fundamental. Okay. Now, let us try to find the number of cycles that each signal will complete over the time period of the added signal. Okay, so let us see this. So time period of the resultant waveform is, we have seen, we are continuing with that example, and the time period of the resultant waveform is, say, 0.02 seconds. Then we can calculate the number of cycles each waveform completes during this cycle. How do we do that? That is simple. N1 into T1 is equal to T. So N1 will be equal to T divided by T1. Now T is 0.02 and this is divided by T1. So T1 is 1 by 100. So this gets multiplied by 100 and you get 2 cycles. What does it mean? It means over the time period of the resultant, the first waveform completes 2 cycles. That means in 0.02 seconds, the first waveform will complete 2 cycles. What about the second waveform? That is N2 into T2 is equal to T. So N2 will be T by T2. So that will be 0.02 multiplied by 150, 3 cycles. So the second waveform will complete 3 cycles over the time period of the resultant. And finally, the third waveform X3T, N3 into T3 is equal to T. So N3 is equal to T by T3. So that is 0.02 into 200. This will complete 4 cycles. So note that this particular example is such that all the individual waveforms are completing integer number of cycles over the time period. And that is why the resultant is a periodic signal. So let us verify this by writing a MATLAB program and plot all these signals. So we'll plot x1, x2, x3, and finally the addition of these, and verify that the time period of the added signal is indeed 0.02 second and over this time period, how many cycles each individual signal performs. That is what we want to see. So you, as usual, clear CLC, CLF. F1 is 100, so T1 is 1 by F1. F2 is 150, so T2 is 1 by F2. F3 is 200, so T3 is 1 by F3. Now you, since it's a continuous time signal simulation that we are doing, we choose a sampling frequency which is much larger than the highest frequency in the signal. So that is 200. So we take 100 times F3, and therefore our sampling time is 1 by Fs. Then we generate our time vector and now generate all the signals. So x1 is 2 pi f1 into t, x2 is sine of 2 pi f2 into t, x3 is sine of 2 pi f3 into t, and x is summation of all these. So once you have got this, now it's a question of simply plotting the waveforms. So I'll not go too much into details of this. You can just probably pause the video and look at this in detail, but we have often discussed how to plot the waveforms, etc. So I'll not take too much time in explaining this, but let us look at the waveforms which are plotted. First, look at x, which is the resultant of addition of x1, x2 and x3. And we have seen that its time period should be 0.02. So is it 0.02? So in fact, we have chosen our time period such that it completes 2 cycles. So you can see in 0.02 it starts like this, okay, varies like this and becomes 0 at 0.02. Now if you compare this part with this part, you will find they are completely identical. So which tells you, so we have plotted only 2 cycles of x, but it can be extended to any, because we have taken 0.04 second as our last time for the time array. That is why it is plotting 2 cycles. Okay. Now over this 0.02, let us look at each of the waveforms. X1 you can see completes 2 cycles. So 1, 2 over 0.02. X2 completes 3 cycles. So you can see this 1, 2, 3, 0.02. And X3 similarly you can verify that X3 completes 4 cycles. Okay. Let us now turn our attention to discrete time signals. Actually, the treatment is very similar to what we have done for continuous time signals. Only difference being that there we talk in terms of time periods which are in units of time, maybe seconds, microseconds, whatever. Whereas when we are talking about discrete time signals, the time period of the discrete time signals is expressed as number of samples. So for discrete time signals, the period is expressed in terms of number of samples n rather than the time t. So sum of discrete periodic signals is always periodic, since the ratios n1 by n2, n1 by n3, etc. are always going to be rational. After all, when you take any individual periodic signal which is a discrete time signal, you specify its time period in terms of n samples, and these are necessarily an integer. This value is necessarily an integer. So when you take n1 by n2, n1 by n3, these are always rational. So if you have got number of discrete time signals which are periodic, and if you add them together, the result is always going to be a periodic signal. And the technique of finding time period is similar to continuous time signals, except that you now find n1 by n2, n1 by n3, etc. rather than t1 by t2, t1 by t3, etc. So let's take an example. Suppose x1 is sine of 2 pi n into 1 by 8. So this I had taught in one of my earlier sessions, and just note that in this case, if you remember, the parameter for the sine wave for the discrete time signal was 2 pi n k divided by n, capital N. So in this case, k is 1, capital N is 8, and that 8 is the number of samples after which x1 repeats. Now if you take x2, then that is sine of 2 pi n 1 by 16, which tells you that 16 is the number of samples after which x2 repeats. So n1 is 8, n2 is 16. So if you calculate n1 by n2, that is 8 by 16, that is 1 by 2. Since there are only two waveforms we are considering, there is no other ratio. So here it's easy to find the period of the sum, that is 2 times n1 itself, that is 16 samples. So what does it mean? That if you have a discrete time signal which has got a time period of 8 samples, and you add this to another periodic signal which has a time period of 16 samples, then the resultant of addition of these two will have a period which is still equal to 16 samples. So we are going to verify this through a program. So let's look at the program. So clear CLC, CLF, N1 is 8, N2 is 16, then N is from 0 to 32, because 16 is the number of samples after which the resultant repeats. So we want to see at least 2 cycles. That is why we have taken 32 samples here. Then x1 is sine of 2 pi n divided by n1. x2 is equal to sine 2 pi n divided by n2. X is equal to x1 plus x2. And then you plot. But since it's a discrete time signal, what you do is you do what is called as a stem plot. So n x1. But so stem plot actually completely describes the discrete time signal. However, to see the nature of the waveform easily, what we have done is we have held on to this, and then we have plotted also. So the plot function is not absolutely necessary, but we have used it in order to show the nature of the waveform comparatively easily. Okay. So you can plot x1, you can plot x2, you can plot the resultant, and if you do that, this is what you will get. So as I said, your x1 repeats after 8 samples. You can see this. So this is 1, 2, 3, 4, 5, 6, 7, 8, and then it repeats from here. So that is your x1. x2 you can count, say 0, 15, and then it repeats. Okay, so this has a time period of 8 samples. This is a time period of 16 samples. Now if you look at x, you will find that up to 16 samples, this is the nature of the waveform, and after 16 samples, this nature repeats. So clearly it shows to you that x is periodic with 16 samples. So basically the previous example that we worked out manually, analytically, we have verified through this program. So this was a short introduction to periodic signal, and that is all in this session.